And the first, this is Unit 1, the first part of Unit 1 is kinematic relationships. So this thing is called, this section is called kinematic relationships. And the first learning outcome we're going to look at is derivation of the equations of motion using calculus methods. Okay, now if you've got a pad or a jotter or something, just use your physics jotters if you've got them, maybe write some notes down. These, right off the bat, what we're doing now could be asked for in the exam. So, and these derivations do cause a few problems because they're relying on you having a fairly decent grasp of your higher maths. If that hasn't scared you off, we'll batter on. Just want a couple of little simple things. One is definitions of velocity and acceleration, but using a kind of calculus notation. So let's just write down, so velocity, what is meant by velocity? Right? I'm sure you'll know this. I would normally ask you guys at this point in a classroom, but we'll just give you a think. What is meant by velocity? So velocity is defined as, have a think, see if we can figure out the next one, the rate of change of what? Okay, a second to think. Velocity is a vector, so it's going to define the vector. So velocity is the rate of change of displacement. I'm going to write in here as a wee with respect to time. Right? That will often be written as WRT. Okay? But it's obvious, okay? We don't write double T there. But I'm just going to put it in there. Now, how do you get that? So let's say, so velocity equals, it's the change in displacement over the change in time. I understand that, that's fairly straightforward. And then what you can do is, that's called the average. So it's the average velocity, the change in displacement, the change in time, or the time it took to change the displacement. Fairly obvious. But what we want is an instantaneous velocity, not an average velocity. Now, if you remember back to your third year physics or fourth year physics, you'll remember the way you get down from an average velocity to an instantaneous velocity is by making the time really, really small. The smaller you make the time, the less time the object has to change velocity. So you've got more chance of whatever velocity you end up with, that's its velocity at that instant. Okay. So what that means is, so for V instantaneous, now you don't always have to write instantaneous, but for this line only, I'm going to write V instantaneous, but whenever you see as V, assume I mean instantaneous velocity, right? For instantaneous velocity, you take, it's called, and you might say this in maths, limit of delta S to delta T. In other words, when you make time is taken to the limit of smallness. Now that's not a technical term, that's just my way of looking at it. So any smaller and there wouldn't be a time, it just would cease to exist. Nothing is time is zero. Alright, so making time is theoretically how small can I make time so that it still is measurable, but it's so tiny there's virtually no way that the velocity can have changed over that time. It's just impossible. And the way you write that mathematically is saying that, well, time is tending to zero, so delta t, the way you write that mathematically, tends to zero. And you say, right, okay, what does that mean? Well, that means you got V, and the way you express that is you say, well, V equals, you don't write limit delta S over t, you write that as ds by dt. Okay, and that's what that means. So that's velocity, and you probably recognise that, I'm hoping, from maths, that looks like differentiation and integration, because it's a big part of it. So velocity is ds by dt. That just means the rate of change displacement with respect to time. Done. Okay? Now, you can do the same thing with acceleration. So acceleration, let's change colour again. So acceleration, oh, hang on, I'm in the wrong setting, give me a moment. Get the pen. Acceleration equals the rate of change of 1, 2, 3 velocity with respect to time. Okay, so with respect to time, so again, the same thing. So A average, I'm sure you'll find this nice and straightforward, is, what's A average? Say to yourself, that's right, delta V over delta T. So that's the change in speed over the change in time. Usually that's written as V minus U over T, but it's the same thing. Okay, but we want A A instantaneous, and I'm just for this case only, I'm going to write A instantaneous, and that's going to equal the limit of delta V to delta T, where delta T tends to, that's what the wee arrow means tends to 0, right? Not 0, tends to 0, and at that point, that leads to A equals D, what is it? dV over dt, and that means acceleration is equal to the rate of change of velocity with respect to time. So that's what this bit here. All right, so these are two things you have to know. If you look back at this is derivation of equations of motion using calculus methods. So first thing is derivation of, so derivation 1. V equals u plus at. So when I try and get to v equals u plus at using, and not the higher method, I don't know if you remember the higher method, it's a different method this. So what I say is, you're often given this, so given, this is how it's worded, given that A equals dv by dt, or in other words, we've just done that, alright, show that v equals u plus at. Okay, now what? So that's what you get in the exams. That's the question you get in your prelims, your unit tests. What do you do with that? So what you say is, you say, okay, so dv over dt, I don't know why it's done that way anyway, and then you say you integrate both sides. So you integrate both sides of that equation. Remember in mathematics, that as long as you do the same thing to both sides, it's okay. So we're integrating both sides with respect to time. Okay, don't put a wee line in there, that's just to show you, just to highlight that. So we're taking both sides with respect to time, and we just, so therefore, now here's a thing you won't admit before. If you integrate, see that looks like derivation, integration of, so we integrate this dv by dt part, that just becomes v, okay? If that's just, so you're integrating that because this goes to v, and this bit here, if you integrate that, and if you remember, A is actually just a constant because I'm integrating with respect to t. There's no t in here, right? I don't see a t. So you have to. So when you integrate, if I integrated, let's see if you can remember. If I integrated the number 4 with respect to x, you're all happy that becomes 4x plus c. Yeah. So because you don't actually do anything to the 4, you just add an x in. So in the same way here, you say, okay, that means that's going to become, because it's respect to t, it's at plus a constant. Now it's starting to look familiar already, but here's the thing that's challenging. How do you get rid of the constant? And so here's what you say. You say, right, okay, and it's the same trick for the next proof as well. When t equals 0, v equals c. Well, that makes sense, because if you make this equal to 0, you get a times 0 plus c. So this bit just disappears. So that bit becomes 0. So when t equals 0, v equals c, and when t equals 0, by definition, v must equal u. Okay? So, because it's the velocity you're dealing with must be the initial velocity. If time hasn't happened yet, the velocity you have that you're measuring and you're looking at is the initial velocity, because you've not had time happen yet. No time's gone on. So that velocity is the initial velocity. So c equals u. All right? Therefore, v equals at plus u. In other words, v equals u plus at. All right? And that's it done. Fine. So that's a derivation you have to know. I'm going to put in here, learn this derivation, because you can be asked for it. Okay? Right. Now, I'm going to go to the next one, derivation number 2. Now, this is a short little video just to get us off the ball, off the ground. And you have no problems to come on this, but that's on its way, don't worry. Okay, derivation number 2. And this is for s equals ut, plus a half at squared. All right? So what you say here is, and this is what it's given, you say given, this is what you state before you actually do the question, given that ds by dt, what does ds by dt equal? All of you should be saying to yourselves, it's equal to, That's right, V, show that S equals ut plus a half at squared. Okay, so what do? You say, right, I'm going to integrate both sides. So I know that integral of ds by dt equals integral of v with respect to dt. Sorry, so far. So this bit here, this section here, when you integrate ds by dt with respect to t, you get s. So s equals, and this is where it gets a little bit complicated, not massively. We don't use v. We don't go to vt because plus c, it doesn't get us anywhere. So what we say is, okay, let's integrate. And rather like v, remember, v equals u plus at. You've just derived that. So put that in. You get integral. That's not an s, remember, this is an integral. I'll put it maybe a wee bigger so it looks, oops, hang on. It's a bit small. Try that again. I hope you enjoy the multiple colours here. That will be u plus at brackets dt, it's an a. You do that, that becomes integration by parts. So that's integral of u dt plus integration of at dt. All right. Now don't worry if you're panicking because you'd have done this in your higher maths exam without a doubt. So that becomes s equals integration of u with respect to dt becomes, what do you think? What do you think? That's right, ut plus, now this is the one that's tricky, now because that was just like this, the u was just a constant, so that was easy just to stick a t in it, but this one has got a t here, see there's the t. Now if you integrate t, do you remember, just to remind you, if you integrate x with respect to dx, it becomes, anyone remember? It becomes a half x squared. You raise the power and divide that new power at the front, so it's 1 divided, but whatever the new power is, you put that comes into here, all right? So in this case, it's going to be a half a t squared. Whoa, wait a minute, that rings a bell, doesn't it? Plus c, I'll back it off, okay? Now, there's a whole mark for doing that, but don't forget doing it, you need 2 parts here, right? So then you think, how to get rid of the c? So, same trick as before. Just change to, I think green's the right colour here to go with. When t equals 0, well if t equals 0, this disappears and this disappears. I'll take that out because you might want to write that down. So when t equals 0, s equals c. Now by definition, if time hasn't happened yet, how far have you gone? Nowhere. So when t equals 0, s equals c, but when t equals 0, s equals 0. So c must equal 0, which is handy. So you get s equals ut plus a half at squared. And that, as I'm sure you already realise, is, let's see, put a wee box around this. That is what you're trying to get to. And you have to, as long as you know these, so again, remember, as I said before, let's change colour, let's go for a pink colour, learn this. Okay, now that seems to, I think that's quite a long, that's not that long, but that's enough for just now. So you get that video. You need to know these derivations off by heart. And the first homework I'm going to give you, which I haven't given you yet, is in the booklet that I've said to look at. Some of the questions ask you to actually derive these equations, so you need to try and do that without looking at the notes. Try your best. Okay? Goodbye for now, and just to make you feel better, there's a picture of the sun. And we'll look at how the sun works later.